Okay, so my name is Karol. Welcome to the second day of Latch-Up. And I have a first presentation today, so let's get started. Today I would like to talk about open source RTL verification with Verilator. I'm from OnMicro. We do a lot of open source services, we contribute to a lot of projects, and we do use open source in our daily work. That's just a short background why I'm here and why I'm talking about the stuff we've been doing. So the projects we're involved with, it's not always just examples, just to give you some background for like why do we care about open source verification and why do we care about having that in place. So we are deeply involved in Calyptra project. Calyptra is an open source root of trust project where we are responsible for doing verification infrastructure. That includes testing, that includes running CIs, that includes automation, all that stuff. But also we do develop the core, the CPU core, RISC-V core that is used there. And of course, every RTL has to be verified, every RTL has to be tested. The core itself is open source, it's a Vir core, available at Chips Alliance organization on GitHub. So we do have to run tests there. And it would be great to have tools for that. The second example is OpenSecura. OpenSecura is an open source chip for like secure tiny machine learning and has been taped out. We were involved there in testing and pre-silicon software development and tools for that. So why do we care about open source verification? So as I said, there is plenty of projects. Some of them we're involved with some of them we're not, but it doesn't mean that they are not there. There is plenty of projects already on the market. There is plenty of code, RTL code that is there, and it's the most popular RTL language there is Verilog. And the most popular testing or verification way of that code is UVM. But there are no open source tools for that, and there is no way to actually run those tests in public. So even though you have open source RTL code, you cannot really verify it with open source tools. So why do we care about enabling this UVM? Basically, to allow that. Yeah. So there is a lot of other open source verification frameworks like CocoaDB, which is great, and I personally prefer it. But it doesn't mean that existing. Somebody said yesterday, like hundreds of thousands of man-years of work would just suddenly disappear. It's not. I mean, it's there, and it would be great to be able to use it, to be able to use it with open source tooling, and then integrate with whatever comes next, with the new methodologies, with the new verification systems, and so on and so on. So we decided to started to work on that some time ago. I will show you some like a history of the project, and we had to choose some kind of a simulator to which will enable, which will contribute and enable the UVM support. So, which is Verilator? It's there for many years. It's a pretty old project, something like 30 years right now. One of the fastest simulator on the market. Open source. Most people use it. I mean, know it. A lot of people use it. So it's a great choice. So we started, and it has a bunch of integrations with many other projects like CocoaDB, with some instruction set simulators, and so on and so on. So great candidate for contributing and extending it to support UVM. So let me just get back and show you what it actually meant to get to the stage we are right now, and what it meant to get the UVM working in Verilator. So first of all, almost 2 years ago, we started with like, let's do that. And the first obstacle was like, okay, but Verilator doesn't really understand timing constructs. So it could run the simulations, but you had to it was limited only to synthesizable Verilog part, and it didn't really understand that something may happen between clock changes, between clock events in your design. So you couldn't really do any like verification, like even run test benches by your own. So we started from that, and to enable that, we had to re-implement the whole scheduler. And around 1.5 years ago, maybe a bit, somewhere around that time, we enabled that. I mean, we contributed that back to Verilator and it was merged. And that one, along with the parallel work on the regular scheduler from Gizalor, enabled, like when both of them were merged, Verilator jumped to like a newer major release to Verilator 5.0. So starting from Verilator 5, you can actually use timing-aware simulation. What does it mean? Well, previously, as I said, Verilator was limited only to synthesizable part of Verilog or system Verilog. Right now, it's not. And basically, before, you had to drive your design from C++ code. So you have to generate all the clocks, all the stimuli from the C++ code. Of course, you could use things like CocoTB that will use C++ to drive your simulation. But at the end of the day, it was as C++ stuff. With the new features, you can do like system Verilog test benches. So you can do super simple things like, clock is not clock after 10 milliseconds or 10 something time units of your design. So you can do things like that. You can basically, you don't have to write your own main C++. You don't have to do it manually. You don't have to drive your simulation from C++. You can run test benches as in the other simulators. And you can try it like that. We just do Verilator --binary, your design to test, your test bench, and it will just generate the main function for you in the background, and you can just run it. Back then, when we were doing the work on the scheduler, we use a pretty nice feature of coroutines. I just mentioned that here. I won't go into details. If you're interested in super details here, you can read the blog note on that. But that actually allowed us to implement all the scheduling, all the asynchronous processing without huge overhead and losing any efficiency or any speed on the Verilator side. It's super useful, super interesting, but if you're interested in super details, we can talk after this presentation, or you can just read that blog note. From the very beginning, we wanted to be transparent with whatever we were working on. So we started tracking features that we were actually implementing, the features that were preventing us from running the full verification or like full UVM stuff. So we created public CIs and public test frameworks where we present results on the dashboards. So it's even online right now, so we can just go there and check the current state of what works, what doesn't, what are the plans, what should be implemented. If you want to join the mission, you can just pick something that is there and start working on that. So what actually was implemented, what exactly was contributed? Here in this presentation, I'm limiting only to the stuff that we did. Of course, there was a lot of other works from other people. I'm limiting just the stuff that we contributed. So first of all, processes. Used extensively by UVM, basically through standard library of system Verilog standard library to control the process that are spawned, so the processes can control themselves. Forks control. So UVM actually spawns a bunch of processes for all those listeners, all those things that generate the data, feed them to BFMs. Gather the results and so on and so on. Parameterize classes. That was like a huge chunk of work because deep in the bottom, UVM is all about parameterized classes. Deep in the bottom, it's a bunch of super generic code with a number of parameters with all the flavors that can actually be there. And once we implemented that, once we got beyond that milestone, we were able to actually verilate. So transpile system Verilog code of UVM library into C++, build it, and start running that. I'm explicitly, on purpose saying start running that because it didn't really work properly. I mean, the simulations were running, but the results were super incorrect. So, but at least we were at the stage where we could start testing what the hell is happening there and what we need to do to get it working. So from the missing features that were there, that were actually compiling and then running, but didn't really work, were even assignments. So basically, you can do something like that, like you have in the example, and that's very, very often in UVM. Virtual interfaces, extensively used everywhere, like within the verification flow within UVM. You don't typically talk to a specific interface. You virtualize them and then talk through a generic implementation from various parts of your verification code. And of course, a bunch of other features, like a bunch of other smaller cases here and there, smaller bug fixes, smaller adjustments here and there. So things like unpacked structs, semaphores, all those stuff, which seem not that hard, but in the end, if you have like a tons of them, it's super painful to implement all of that. One of the biggest recent developments is actually enabling constraint randomization, also used extensively. Maybe it's not a part of UVM per se, but used extensively with those type of testing, with those type of verification to extend the coverage of the test suites. We actually had one approach back in the days, like a year ago, something like that, with Crave, with integrating Crave, which is a library for C++ library, system C library for constraint randomization. That didn't work well back then because we had a bunch of race conditions and stuff like that, and didn't have enough time to focus on that. But we changed the approach recently and implemented it in a way that Verilator actually generates SMTLib2 description of the constraints and then passes this description to external solver, any solver that actually handles that. So we can use a bunch of them from your system. Just run this underneath, get the results, and use them in the simulation. It's maybe less effective at this point, but we have to start with something. And it was way easier to implement it like that. And then we can, of course, switch to something more integrated and faster. It's not yet merged, but as I checked that today, like an hour ago, all the tests are green. The last round of a review from Wilson is addressed, so hopefully it will be merged soon. But if you want to use it today, you can grab a branch that is in this PR and then just use it there. Of course, you can read more on that. We have a blog note on that if you're interested. Just go to our blog and check it there. Another ongoing work and already pull request. This is some initial work on system verilog assertions. I get a lot of questions on that every time I do some presentation on system verilog. This is like just a small piece of that. Basically, right now, implementing assert off, assert on, and assert kill. So basically, things like you can, for certain task in the system, you can disable, enable assertions, and that's it for now. Of course, more to go, more to come, and it will be worked on. There is a PR that PR still needs some work, but it works. You can use it. You can just grab this branch and then why not? During the work, we of course also developed some additional tools, additional scripts and helper tools. One of them is ASCII. ASCII is actually a generic tool for viewing or observing and debugging AST trees. So if you are working on any parser, compiler, stuff like that tool, it may be really useful for you. We have an integration with Verilator, so we can use it directly with Verilator. It's already there. There is a GDB plugin or GDB extension that allows you to use that. And in general, it works like that. So you basically can, this is an example from Verilator. So we can do something like dump AST tree at this stage, dump AST tree at this stage, and show me the difference. So basically, it's super easy in the end to basically track the changes in the AST tree on certain processing stages of the like transpiling flow, because in the end, Verilator is mostly about operations on AST, and in the end generate a C++ code from that. And that's super useful. We can actually bind it into GDB and just do a breakpoint, 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 and in between the breakpoints just run a command, show me the difference in the AST, and you get something like that. It's even colored, so it's really, really easy to check what happened and track down what the hell is not working there. Again, open source, again, you can just grab it from GitHub, use it, not only with Verilator, but with any work on abstract syntax tree if you do that. Okay, so having all that in place allowed us to actually get to UVM tests, UVM test benches working in Verilator. An example of that you can find in Vir. This is the core I mentioned at the beginning, used in Calyptra project. In the Calyptra project, there is a test bench running in the GitHub CI that uses UVM. So the test bench itself, like, it's super simple because it just writes to memory, reads from memory, nothing really fancy, but it uses all the UVM things that if you are working with UVM, you're used to those agents, monitor drivers, scoreboards, sequencers. So it does use all those features, proving that they actually work in Verilator. And this is run in public CI without licenses, and so on and so on. If you want to use it, free commands, and that's yours. It's kind of with asterisks. You may need to compile Verilator from sources, because as you can imagine, this is pretty new code in Verilator. Depending on the distro you use, you may not have this version yet in your system packages, but Verilator is not that hard to compile, so you can just build it from scratch, and you will have it. You can just use it. You can run it. And with those three simple commands, you can have a UVM, open source UVM running on your computer. So if you run it, it will basically do all the stuff for you, and you'll get something like that. If you are used to UVM scoreboards, this is the results. And actually, this is exactly the same result that you would get with proprietary simulator running the same code, the same UVM test. Maybe, actually, no, this is like byte to byte or character to character, identical to whatever you get in proprietary simulator, which is super cool. Finally, we have something that we can run, and then we can run it at a scale. We can run it in public CIs, and we don't have to hide the results. That's really, really, really useful. So what's next? So of course, a bunch of other. Bunch of new stuff to be implemented, and more test cases in general. Basically, if you have something that you can run it with, please do. You'll probably find some bugs, you'll probably find some limitations, but the more test benches, especially those that are open, we have, the better. Then we can actually track that, and then we can actually figure out what is missing. But also, we need to do some work on optimization, like especially optimization. This is already happening. We do work on optimizing that, but there is still some stuff to be done, like, for example, on the compilation side. UVM is huge, so if you generate a C++ code from it, it takes a while to actually compile it. A while in like minutes. Maybe it's not long for RTL development, but for a computer scientist, if something takes more than 10 seconds, I forget what I was doing. So, it has to be faster. I mean, computers are fast, so it should be faster. And of course, more features that we already know of that we have to add. And more test benches, we know at least of a few of them, like running full Calyptra test benches, because right now we run mostly the CPU test benches in that, but there is more we know of. There is RISC-V. So right now, with the constraint randomization in place, or in place soon, TM, we should be able to run RISC-V and then run open source verification, of course. Like, I know that OpenTitan uses RISC-V extensively. We use that in Vir and many other projects. So that's actually something that may be super useful. So what is actually being worked on, and you should expect it soon. So first of all, dynamic array randomization. There is already a pull request with some initial work on that open in Verilator. So a bunch of various new various type of randomization in System Verilog. It's like actually super messy in System Verilog. I mean, like you can randomize anything with anything. So it's a lot of combinations to be handled. Per process random generation. System Verilog actually assumes that every single process can have its own, has its own random generation, and you can control it. So this is not yet there. We have to implement that. And inactive region, so basically delay of 0, which sounds weird, but right now it's implemented as delay of 0, so basically it pauses the simulation but immediately restarts it. But in fact, it should move the scheduler, the code to be scheduled in the next slot, in the next piece of the scheduling flow. So, in this example, this should not stop. Or it actually, yeah, it actually should stop. Yeah, so, no, it should not stop. Yeah, sorry, because it should not. But in Verilator, it would stop right now because it's not scheduled exactly according to IEEE. So that's all. I don't think we still have, I suppose, like a minute maybe. Thank you. There was a mic, but somebody took it. Okay.
Is on?
I have a question, which is, when you add these capabilities for delays and timing constructs and so on, how do you do that without compromising the speed of code that does not use any of those? In other words,
that's a great question.
Verilator is using the fact that it is synthesizable without these dialing to analyze and optimize the code. Mm-hmm. Is it possible to mix and match? That is, the DUT can be compiled without those constructs? And
So that's that. Like if something doesn't really use any delays, it is compiled without those options. So like transport, basically, the C++ code doesn't really use that during the generation. So that's that. But if you explicitly don't want to use any timing stuff, like even if you have delays but you just want to ignore them, that's still a default.
There's a command line flag to ignore.
Yes, and actually default Verilator behavior is not to use them, to ignore the delays. You have to provide -- timing to actually use the scheduler that we added that is timing aware. It is slightly slower, like few percent slower than a regular.
Actually, I don't think it's a default. Right now you have to say either timing or no timing.
Oh yeah, exactly.
Now it is.
Right, yeah.
But the question is, can you mix and match those? Can you compile part of the DUT with no timing and the VM with...
Then you provide -- timing, and if you don't use delays, it will default to the other scheduler. So it won't use delay constructs within.
I'm asking a slightly different question. I have a DUT that does not have any of these things, and I'd like to compile it with no timing. I have UVM that does use timing, and I want to compile it with timing, and I want to mix and match those. Is that okay?
There's no support for that right now.
The whole thing has to be compiled either with or without.
You would have to do something like validate the code without timings, validate the code with timings, with timings, with timing, and then somehow glue them together in C++ level. Like do two libraries and glue them together. The only problem is that they would be totally independent. They would use two different schedulers, and you will have to synchronize them in your top level. Yeah.
Thank you. I think you can ask all more questions in the break. We have time for more questions. Thank you again.
Thanks.